Alright guys, today by request we are going to talk about simplifying radicals, and the biggest thing about simplifying radical expressions that I think we need to start with is this concept of the product rule. And what it says is, if I have the square root of a product of two numbers, or really of one number that can be written as the product of two numbers, then that must be equal to the square root, or the product of the two separate square roots multiplied together. And if this doesn't make sense, let's look at a specific example. So you can see at the bottom it says, let's try when a is 9 and b is 4. The idea is, if I take the square root of these two numbers separately, 9 and 4, then I would get 3 times 2, which is 6. But if I were to take the square root of 9 times 4, order of operations, do the inside first, well, the square root of 36 is 6. It doesn't matter which way I do it. And this is super powerful, and hopefully you already see the connection to how this helps us simplify radical expressions that are more complicated. So let's look at some of those. It seems in class that we are pretty comfortable, or that you guys have been using these factor tree ideas a lot. And while that's great, the truth of the matter is I don't really care about all of the factors of 180. That's not the point. What we want to know is, does 180 have any factors that are perfect squares? If I don't have any perfect square factors, then I'm not going to be able to simplify, and so I don't care about what the factors are otherwise. So I want to kind of encourage us to, especially when we have larger numbers, to not just look at all the factors of 180, but just look at the perfect squares and see if they are factors, right? So we have these perfect squares we know, hopefully we know, right? We have 4, 9, 16, 25, 36, 49, 64, I lost my spot there. That was 8, 81, 100. We should be able to go at least up to 15, all of us. Now, obviously, not all of these are going to pertain here, but the idea is I should be able to quickly look at these numbers or scan through them and see if any of those will go in. Right? It appears 4 does, but the bigger the better. Right? So 9 looks like it's going to go in. So what if I try rewriting 180 as 9 times some number? 9 times 20 works, so that would mean that's the same as the square root of 9 times the square root of 20, which is 3 square root of 20. Now I should always check if the number on the radical is not prime, I should see if there's any more perfect squares. And 20 is indeed a product of two other factors, 4 and 5. And so the square root of 4 is 2, so we have 3 times 2 times the square root of 5, which is 6 square root of 5. And that works. Right, and I want to compare this method to what if we were trying to find all of the factors and then test them. Right, so this is kind of what you guys are doing. Okay, I'm thinking, okay, square root of 180. Well, I could write that as 2 and 90, so I could write it as square root of 2 times the square root of 90. But the square, let's see, perfect square is 90 could be 9 times 10. So now I have 3 times the square root of 2 times the square root of 10. And 2 can be, or 10 can be 2 and 5, and so here I get a pair of 2's, so 3 times 2 is root 5, and 6 times root 5. We can still get there, but I think it's faster if we check with the perfect squares first, right? Instead of finding all of the factors, going the other direction with it. Of course, this will work, and maybe I made this seem a little longer than it needs to be. Maybe as I scanned through, I got 2 and 90, and 3 and 60, and 4 and 45. You could approach it this way, right? And like 6 and 30, and then maybe 9 and 20, and 10 and 18. So maybe you can list all the factors and find where perfect squares are and pick larger ones, kind of like we did. But the point is, 2 and 9, we don't care about those because none of those are perfect squares. So why don't we just start with 4 and 9 and scan through that way? So let me show you. Let's look at some more examples. And I think that the method I'm suggesting is especially powerful when I have larger numbers, right? The square root of 245. We could go through all the factors of 245 for days, right? So why bother with all that? Let's just test. Is 4 going to go in? No, it's not an even number. I hope we know like this rule, but 2 plus 4 plus 5 is 11. If in order to be divisible by 9, all digits have to add up to 9, which this doesn't. If you're unsure of that, we can test it, right? We could like try dividing by 9, and it goes in 2 times, and that gives me 18, and 65 is certainly not divisible by 9, so 9's out. We can keep going. 16, again, that's not going to work because it's not even, so that's not going to go into it. 25 is close, but 250 is the closest that goes into 25. 36, nope, because it's 4, was it? 49, that might be interesting, right? Because if 50 times 5 equals 250, then 49 times 5 would equal, you got it, 245, right? So the square root of 245 is equal to the square root of 49 times the square root of 5, which is 7 root 5, and we're done. This is, you may disagree, but I really think this is easier than me going through and saying, okay, let's see, 245, that's like 5, I know 5 goes into it, so let's see, 5 goes into 120 times, so that's 40, and I guess if we'd have done it this way, we'd have gotten lucky because of 49, but the point is, I actually don't care which method. I want us to be comfortable with both because we need to know what we're looking for. So let's look at 108. Again, 4 appears to go into it. It does, definitely, right? 4 times 27. And so we could stop right there and say, okay, square root of 4, square root of 27 is 2 root 27. The square root of 27, we know some factors of that are 3 and 9, so square root of 9 and square root of 3. So we have 2 times 3 times square root of 3, which is 6 root 3. I do want to encourage you also, though, sometimes not necessarily to stop at the first perfect square you see. So maybe you say, oh, 4 works, but I wonder if the next one works. What if I tried 9? And we know, for instance, that 9 times 10 is 90. So if I added 2 more 9s, then 9 times 12 is 108. So maybe you say, okay, maybe that would be easier. Square root of 9 and square root of 12, and square root of 12 may be a little easier for you to break down, so we get 6 root 3 that way. And again, I don't care which way we do this. I just want us to get better at it and more efficient with it. So I want to expose you to some different ideas other than a factor tree. Let's look at just one last one. Hey, okay, I don't know what just happened, but I want this to pause. All right, so last one. I don't know if it ever paused or not. I'm sorry if it didn't. The square root of 112. We can, again, maybe try some factors. 4, I'm pretty sure, is going to go into this. 4 times, well, again, and some of us need to work on this. 4 times 25 we know is 100. So I would need 12 more, and 4 times 3 is 12. So that means 4 times 28 is 112. We could stop there, or I could notice, hey, there's a 4 into this as well. So square root of 4 times square root of 4 times square root of 7 gives me 2 times, oh, wow, what's going on right now? We have 2 times square root of 7. And that gives us 4 root 7. Okay, so that's it for simplifying radicals. I hope that helped, and obviously we're going to keep practicing this in class.